Is it all right? Is it all right now?
Welcome everyone. So we are going to start our first session that is on fuels for sustainable transport. So in this session, there are two moderators for this session. The first moderator is Professor D.G. Sharma and Professor Abdul is the second moderator. So first I will introduce them. So Professor D.G. Sharma is a mechanical engineering graduate from MIT Jaipur. After working with CIM Limited, he joined Roorkee University for post-graduation in thermal engineering. Dr. Sharma joined MIT Jaipur in 1992 and is currently working as a professor at HEG. He published more than 150 research papers, 15 books and several book chapters, and he has also filed 7 patents. And the second moderator, Professor Atul Dhar. So Dr. Atul Dhar is currently working as an associate professor in IIT Mandi. He completed his master's and PhD from IIT Kanpur. Professor Dhar was awarded with Young Scientist Award from International Society for Energy, Environment and Sustainability. His areas of interest include internal combustion engine, emission control technologies, alternative fuels, and replicating oil technologies. He has published more than 50 research papers in international reviewed journals. With this brief introduction, I would like to hand over this session to our moderator, Professor D. Sharma.
Yeah, thank you, Nick. I'd like to welcome all of you to this session of Set 6, session 1A. And we have our first panelist, Professor Kirti Bhushan Mishra. He is assistant professor in the Department of Mechanical Engineering and Industrial Engineering in the Institute of Technology, Roorkee. Dr. Mishra has more than a decade of research experience in the area of combustion, fuels, and fire safety at a world-renowned research lab in Germany. He has extensive hands-on experience in measurements and modeling of various life cycle combustion-related problems. Apart from 21 international patents, 29 journal papers, and 48 conference papers to his credit, he also carries substantial experience in managing national and international projects. He is a founder of Track Technology Risk Research and Analysis Group Lab at IIT Roorkee, where small-scale combustion tests on various alternative fuels can be performed for initial screening. His areas of interest are alternate fuels, combustion, emission control, fire, explosion, and CFD modeling. So I welcome Professor Kirti Bhushan Mishra to give his presentation.
I hope I am audible to all of you. I hope I am audible to all of you. Okay. So this is the way I usually deliver my lectures at IIT Roorkee. Students always say that you have good voice to present the lectures without any microphone. So I'm following the same technique here. First of all, thanks a lot for having me here. This is the third time I'm participating in this prestigious conference. And the work which I'm going to present today will be a sequel of the earlier presentations. So those who were present in the last two conferences, they can memorize that the work which we are doing is focusing mainly on what happens when we use conventional as well as green fuels with some blends and observe their performance and emission parameters in a laboratory scale engine and in a realistic science engine. So until last year, we were able to perform some experiments with these fuel blends at our laboratory in IIT Roorkee, which has a small engine. This year only, one of my MTech students, Boyri Mahesh Yadav, he took this initiative and went to a company where we have a larger size engine, and there we tested the same fuel blends. Actually, these fuel blends are one of its a novel kind because it contains the oxygenated fuel as well as C10 improver at the same time. So what we get as an output is maintaining the engine power and reducing the emission at the same time. So this is what will be the major content of my talk today. So we have learned over the years that the pollution in our national capital mainly comes from transportation sector, where we emit a larger fraction of the pollutants from heavy-duty trucks, followed by two-wheelers and then passenger cars. So we are mainly talking about the particulate matter oxide 2.5, sulfur dioxide and NOx. So these were the three main constituents which we focused upon, and we picked up some fuel blends, tested them in the laboratory, and then went to a larger size engine. The fuel blends which we have chosen are belonging to the conventional fuels like diesel and green fuels like biodiesel, ethanol, methanol, and at least one C10 improver. Objective is very clear that we want to reduce emission without compromising with the efficiency. So what we foresee is that these fuel blends can be immediately utilized in the existing vehicles present on road, and they can be also seen as one of the possible alternatives fuel in process industries. So here what we see is typical kinds of biodiesel. The feedstock were listed in the earlier presentation also, and here we have maintained that uniformity, took waste cooking oil as our main biodiesel fuel, together with ethanol and methanol, and one of the C10 improvers. So we picked up this DTBP as one of the C10 improvers, and we varied the contents in the same way like in our laboratory scale. So why engine size matters? This is what you see is a three-wheeler having a capacity of 5 kilowatt. This is all-terrain vehicle having a capacity of 15 kilowatt, tractor 25, and one small goods carrier which has a capacity of about 60 kilowatt. So when we look to the laboratory scale engine, this is something like this. And what we did in the present work is we extended our testing up to this range of engine capacity, 15 kilowatt. This is a schematic of laboratory scale engine, which has a capacity of 4 kilowatt, single cylinder, and 611 cc. This is just a recap of what we did earlier. So we measured all these characteristics NOx, CO, and smoke in the laboratory side engine. And what we found out is with the ternary blend, having biodiesel as 93.2%, DTBP 1.8, and ethanol 5%, gives us the best results, comprising of 6.3% NOx reduction, 52.4% CO reduction, 49.2% hydrocarbon reduction, and 45% smoke reduction. So we targeted that let us test these fuel blends in a heavy size engine and then see what comes out. So we contacted one of the companies located in Pune, Apex Innovation, and they have got this 22 kilowatt double cylinder turbocharged engine where we tested our fuels. The major properties what you can see for all these fuels have more or less a range of heat of combustion from 22.7 megajoule to 36.6 megajoule, and they have various cetane numbers. So what we wanted to see is how we can utilize the energetic fuels in a small quantity to enhance the property of biodiesel and diesel in small scale as well as large scale engines. So this is our cetone improver DTBP, which has a chemical structure something like this, and we want to improve this cetane numbers of diesel and biodiesel by adding a small quantity of DTBP together with ethanol or methanol. So this particular peroxide has a very nice burning characteristics. It has a chemical symmetric chemical structure, and when you burn it, it burns at a higher rate, produces less smoke, and shows kind of transparent flame. So this can help us to improve the cetane characteristics of diesel and biodiesel. Over the years, we have learned that if you burn biodiesel in the engines, it produces more NOx than diesel fuel. So when we are targeting that at least 5% of biodiesel should be added in the existing engines by 2030, then we have to look towards what happens when we increase the quantity. We go beyond 5% and see how these fuel blends are performing. So we started with engine calibration. We compared the experimental results obtained from small scale test and then large scale test. So what we saw was we have a deviation, but they are acceptable because the large scale experiments can also go with the scale. So this is what you see is the result for carbon monoxide, and at the same time we have also measured NOx emission for these two sizes engines, and what you can see is biodiesel in both cases emits more NOx than diesel fuel. So we wanted to test biodiesel alone in the largest scale engine, but we had some problems. After a certain time period of some minutes, the engine got stopped. So we took out the injector and we saw that it was stopped. So we decided that let us not go with 100% biodiesel, decrease the quantity up to 50%, and then see how the blends are performing. So in all these experiments, what you can see is we have maintained the RPM at 1600 and tested the different fuel blends. So in 15 kilowatt engine, what you see is both diesel as well as diesel plus biodiesel, 50-50. Both are producing the same brake-specific fuel consumption. That means there is no change in fuel quantity that is required to produce a certain power. If you look at the carbon monoxide emission, in case of diesel we have much higher, but in case of mixture of diesel and biodiesel, we have drastic reduction in CO emission. In 50-50% of biodiesel and diesel, we have got higher efficiency than the diesel alone. So this indicates that we can use 50-50 blend of diesel and biodiesel, provided we have that much biodiesel available in the country. So once we perform this test, then what we get to know is, are there some decrement in efficiency? Are there some enhancement of emission or not? So small scale experiments may not provide you all those answers, so it is necessary to scale it up. Now let me show you some of the results of fuel blends. So what you can see here is different fuel blends, starting from diesel alone, biodiesel alone, and then biodiesel DTPP, biodiesel DTPP plus ethanol, diesel alone, and then the same thing with 50-50 proportions. So we maintain the 50-50 proportion of diesel and biodiesel and included ethanol and one C10 improver, that is DTP. What we observed was, in all cases, the emissions, CO, NOx, efficiency, all cases, we have excellent results when we use these fuel blends. So the laboratory scale results were reproduced in moderate size engine test also. This fuel blend with ethanol 5% and some percentage of DTPP reduced the CO NOx up to a great extent. However, we have got a little bit increase in fuel consumption in this blend, but looking to the rest of the advantages, this can be thought of that yes, we have to put in a little bit more fuel than what is required for other fuels with higher level of emission. So 46.6% of diesel, 46.6% of biodiesel, and DTPP and ethanol in small quantities have produced a reduction in NOx, CO, smoke up to a level of 20 to 50%. So this is what we wanted to make sure that whether the engines which are present on roads can also produce the same outcomes or not. What you can see here is the comparison between diesel fuel and the best blend of biodiesel. So in case of all emissions, including efficiency, we have found excellent results, and this reduction in NOx emission, CO emission, and smoke have encouraged us to build some confidence on the tested fuel blends. So what I have shown you or tried to discuss with you is how the scale affects the results from different engines. So the range is not too wide. We went from 4 to 15 kilowatt only, but this gives us a little bit of higher level of confidence that yes, these fuel blends will perform in the similar fashion like in laboratory scale engine. So we had some problems to start the engine, as I mentioned in the beginning. So we reduced the biodiesel content up to 50% and rest were diesel plus other blends. The best blend that we have found was close to 46.6% of diesel and biodiesel together with 5% of ethanol and 1.8% of DTP. And that led us to the reduction of NOx, CO and smoke from 20 to 49%. So this kind of studies are necessary in order to, connect the small scale experiments with the large scale experiments so that we have a better scientific, background to extrapolate the results and give little bit more confidence in saying that yes, the fuel blends are really performing well in the real site engines also. So with this, I have come to the end of my talk. These are the references that I have picked up for this study. Thank you very much for your kind attention. So I'd like to have some questions, or questions can be taken.
So thank you, Professor Vishal. And questions you would like to have after opening remarks by all the panelists.
All right. So I thank you once again to all of you for having me here.
So thanks for starting session with Indian utilization and highlighting the associated challenges. So now we will move on to production aspect of the biodiesel and other liquid fuels. And I will request Professor Sharma to introduce Professor Yogesh Sir.
Thank you, Dr. Atul. So next panelist for this session is Professor Yogesh Sharma. He is a professor in Department of Chemical Engineering in Indian Institute of Technology, BHU, Varanasi. Professor Sharma finished his PhD from Department of Applied Chemistry, Institute of Technology, Banaras Hindu University, Varanasi in 1991. Currently, Professor Sharma is working as a full professor in the Department of Chemistry, Indian Institute of Technology, BHU. His research interests include renewable energy and biofuels, development and characterization of heterogeneous catalysts, synthesis of nanoabsorbents, river health science, monitoring of river Ganga. Professor Sharma is a celebrated researcher in renewable fuels and sustainability with more than 12,000 citations. So I request Professor Sharma to give his presentation, as told by Professor Atul, that he will be talking about the production aspects of biodiesel and alcohols. Over to you, Professor Yogesh Sharma.
Sir,
Professor Sharma, kindly unmute.
I thank you, Professor Dhar, for my introduction. I would like to thank all the organizers, Professor Agarwal, for giving me this opportunity to interact with you. I was supposed to be there physically, but because of some pressing assignments, I'll just start from here today afternoon, say at around 3 o'clock, 4 o'clock, after this session is over, and then we'll be there with you tomorrow. So, can I please request you for next slide? My talk is on fuels for future transport. So, we are working in this area of biodiesel synthesis, characterization, and application in engines for the last approximately 2 decades. And then we find a few very interesting things. If you look at this slide, it presents the world energy consumptions, and then we can see that how world energy consumption is increasing day by day. Can we go for the next slide, please?
Professor Sharma. Hello. Sir, can you please turn off your camera because the data is quite low bandwidth, so it is unable to get.
Okay, good. Biodiesel. See, my talk is basically on biodiesel. I'm happy to listen to the first speaker from IIT Roorkee, who also spoke about this, and is really a promising fuel. Let us see a few things about biodiesel. ASTM specification defined biodiesel as a monoalkyl of long-chain fatty acids derived from vegetable oils. So, biodiesel would be a substitute to petroleum diesel fuel. It is oxygenated fuel. Its complete combustion increases the energy output. It is a better lubricating material. It increases useful life of fuel injection equipment of engine. It is carbon neutral. It is biodegradable and non-toxic in nature. High flash point and high fire point provide handling safety at high temperature, and it is comparable as far as calorific value is there. Approximately 90% of calorific value of the usual diesel, petrol diesel, and it is sulfur-free emissions, like it is environmental friendly, and it has high CPA number. Can we go for the next slide, please? It is like types of feedstocks when we talk about biodiesel. It requires a few things. Say it requires feedstock material, and this feedstock material is responsible for large-scale production of biodiesel, also responsible for its overall cost. So, if you look at the feedstock available for biodiesel, these are divided into three categories: first generation feedstocks, second generation feedstocks, third generation feedstocks, and then these are listed in the slide. All of you can see. If you look at the three, if we look at the first generation, we find that corn oil, soya oil, corn oil, canola oil, sunflower oil, these were the feedstock materials from which biodiesel production started. But then it is started a debate versus fuel. It is expensive. It is limited as far as availability is concerned, and it requires availability. If you go to the second generation feedstock materials, we find that we focused on non-edible oils, non-edible feedstock. So, jatropha oil, kusum oil, madhuka, and there are several other non-edible materials, non-edible feedstocks, where we can focus on biodiesel production. But then if I find that which could be the best feedstock material, then certainly I focus on waste frying oil or waste cooking oil or waste fat from animals. But then they also have limited availability. Third generation feedstocks are very important. These are like microalgae such as chlorella, aspergillus, etc. They are non-food materials, fast growing, virtually go anywhere and everywhere, do not require a land. And then we go for like as per disadvantage. We see that they require advanced processing, and then they are quite. So can we go for the next slide, please? If you look at this, key drivers for future planet stocks for commercial production of biodiesel, we focus on environment, we focus on economy, and we just offer a particular some ideal feedstock that what would be the ideal feedstock. It should be alternative feedstock, non-food or non-rainforest. It should be grown in a short season. It should be highly efficient. It should be its harvesting should be easy. Its handling should be easy, safe. It should be low input as far as growth and harvesting is concerned, and it should be easy conversion to biofuel. So if you look at these, we find several like options, and we finally focus on microalgae. Can we go for the next slide, please? This slide focuses on biodiesel production methods. Like we discussed about the feedstock materials, what could be the better feedstock materials, and then now we focus on biodiesel production methods. Very important because if we have even a expensive feedstock, method is easy, method is conducive. So we have these methods. We have dilution, that is blended fuel. We have thermal cracking liquid fractions. We have micro emulsification, we have process. So biodiesel can be produced from all these methods in four methods. But if I look at the like handling, easy handling, and then easy operation, then I focus on transesterification. It's a very simple chemistry, simple chemical process. Is cost effective and gives high conversion efficiency, 98% of conversion efficiency. It improves the fuel characteristics. It gives out glycerol as a byproduct, which can be used for several other applications in industries, including in pharmaceutics. Biodiesel produced by this method is miscible in any proportions with the mineral diesel. NB and it could be employed to a variety of feedstocks. Rather, all feedstocks it could be employed. Can we go for the next slide, please? India biodiesel history. Government of India launched a national policy on biofuel 2018. We have biodiesel policy, national biodiesel policy 2012. We have biodiesel policy, latest biodiesel policy, biofuels in 2018. It sets a target to blend diesel with B5 by 2030. In 2021, the national average blend rate is estimated to be 0.09%. I recall that Professor Mishra was talking about 5% of blending. Well, it is possible, but then see, tough in the sense that its availability is limited. So, can we go for the next slide, please? Comparison of emission. I mean, Professor Mishra's talk was just crisp and well organized. This he touched there, and then see, I also got some data on this. We are working on this particular area as well. Comparison of emission impacts of biodiesel and diesel combustion ignition engines. So we can see the comparison, what B20 gives us, and then what is B100, that is pure biodiesel. And we find that it is quite comparable. Quite comparable. Can we go for the next slide, please? Comparison of physico-chemical properties of biodiesel and diesel fuel. So, see, this is again very important. We can see the column number 2 and 3, and we find that absolutely compatible, very much compatible. Can we go for the next slide, please? Last slide of today's talk. It is basically, it is not biodiesel disadvantage. It is like research opportunities. Research areas as far biodiesel is concerned. So these are areas where we can work. That is, variation quality, like variation comes from various things. It comes from application of a particular feedstock material. If we go for a very high quality feedstock, we have got a better product. So here we can work that how can we improve quality of biodiesel which is produced from the lowest grade feedstock material. It's not suitable for use in low temperatures because that its flow is affected. Food storage is made from animal and vegetable fat. Increased use of fertilizers. Clogging in engines, no. Regional suitability, strategy, monoculture, and slight increase in nitrogen oxide. Renewable fuel, but then and it results in application results in net decrease of energy. But then increase in nitrogen oxide emission. So, my dear friends, thank you very much for inviting me for this talk. And if there are any queries, I am ready there.
So, thank you, Professor Sarma, for inviting us for the biodiesel production and its quality aspect. So, now we will move on to next speaker, Dr. Amir Mannan. So he will talk about life cycle comparison of various fuels. And I will request all the online attendees as well as the digital attendees to write down their questions and share with us, and we will discuss it after all the opening remarks are finished. So Professor Sarma, please introduce Dr. Amir Mannan.
Thank you, Dr. Dr. Amir Abdul Mannan is a science specialist at Saudi Aramo, Tehran. Dr. Amir Abdul Mannan is a sustainable transport specialist with 15 years of professional experience, conducting corporate strategic research in the areas of energy, technology, and policy for the global energy and mobility sector. He is currently a science specialist in strategic transport analysis team, which is known as STAT, at Saudi Aramco Research and Development Center in Saudi Arabia. He has developed core expertise in life cycle thinking, technology impact assessment, and policy analysis within the climate energy space, particularly for the transport sector. So I welcome Dr. Amir to start his presentation.
Okay, thank you very much for the introduction. My name is Amir Abdul Manan. What I'll be doing today is that I'll be sharing some of the insights that we've gained in my 15 years of doing life cycle analysis for the transport sector. Now, I don't have control on the slides, so I will guide you through the slides as we go along. So the first slide. So basically, just to make sure that we are all on the same page. When we talk about life cycle assessment essentially is a way of assessing a technology or energy system throughout the entire life cycle, from manufacturing, processing, all the way to the final end use. Now, if you look at the red box, typically that's where we measure, which is the tailpipe emissions. But when we talk about, when we're doing comparisons of emerging and alternative powertrains, for example, electric vehicles or fuel cell vehicles or even biofuels, then we're now starting to shift the emissions further upstream. So it is important that we start looking at the emissions throughout the entire fuel life cycle, looking at energy extraction, refining, all the way to operation. But also when we talk about alternative powertrains, there is also a tendency to increase the emissions associated with the manufacturing of the vehicle. So for example, a battery electric vehicle typically tends to be about 30 to 40% more energy or more CO2 intensive than a conventional combustion engine. So we also have to take that into account. So a life cycle assessment is basically a technique that offers a more holistic thinking for us to compare technologies and different fuels and energy type. So now that we have that as the way of thinking about how we assess technologies and fuels, I'll give you some examples of the work that we've done in the last couple of years. So if you move to the next slide, please. Okay, so this is a recent piece of work that we did for China, where we compared the greenhouse gas emissions of conventional engines, hybrids, and electric vehicles. Now, China, just like India, it's a huge subcontinent. Each provinces, each states will have its own power generation, and therefore the power generation can differ from one region to another. So we decided to look at the the greenhouse gas savings that you get with electric vehicles in China by provinces. And you'll see that the regions in red are basically where hybrid electric vehicles emit less CO2, whereas the regions in blue are basically regions that emit where electric vehicles have got lower emissions. Now, the blue regions, for example, in Tibet, Yunnan, and Sichuan, these are regions where the electricity are mainly from hydroelectric. Whereas in places like Beijing, Inner Mongolia, Shandong, these are regions that are still heavily reliant on coal. So in these regions, it makes more sense to have hybrid vehicles with different battery sizes as an opportunity to decarbonize the passenger transport sector. Now, moving to the next slide. Now, the other way of looking at it is that that there is really no technology silver bullet. If you look at this plot here, you'll see that there are opportunities to combine hybrids with advanced combustion engines. So here, what we did was we looked at combining hybrids with a GCI engine, a gasoline compression ignition engine running on GCI fuel. And you'll see that there are significant opportunities to reduce emissions further. The plot on the far right, those are basically the BEV references in Europe. You have the low case and the high case, and then you have the US, again, low case and high case, and again, China, with low case and high case. The bars in green basically shows you the greenhouse gas emissions of hybrids with different battery sizes, increasing the hybridization levels of GCI. generally when you move from a spark ignition or compression ignition to GCI, then you have about 20, depending on your baseline. If your baseline is gasoline spark ignition, then you have a reduction of about 25% for GCI. But then with further hybridization, larger battery sizes, you improve the efficiency, but also GCI fuel have got a lower production emissions, and therefore you bring down the emissions even further up to 40%. Now, electric vehicles also have got the opportunity to bring down the emissions quite substantially. Now, on average, for example, in China, you have about, or even, for example, if you look at Europe, you have about 50% greenhouse gas reduction. However, it also have you have a huge range depending on the states in Europe. So key here is to basically highlight that there is no technology silver bullet. You have to look at it throughout the entire life cycle. There are opportunities with the use of low carbon fuels, as well as combining it with efficient engines. Now, the other thing, when thinking about hybridization or even electric vehicles, we have to start thinking about the critical metals. So if you move to the next slide. So one of the ways of looking at it is, how do we ensure the best use of scarce critical metals? Today about 70% of lithium is produced in Chile and Australia. About, again, 60 to 70% of cobalt is produced in Congo and Australia. And again, about 70% of graphite is produced in China and Brazil. So there are concerns about the accessibility and sustainability of production of battery materials. So the question then now is, for countries like emerging countries like India or even Indonesia, Africa, what are the solutions moving forward? Do we want to compete with all the other superpowers, trying to get access to the limited supply of sustainable critical metals? So what is the best use, given the limitations that we have? What is the best use of every kilograms of lithium or every kilograms of cobalt? So this is one way of looking at it. Now, this is not a full life cycle analysis, but it's a well-to-wheel analysis, which means that we don't take into account of the vehicle manufacturing emissions, but only the fuel cycle emissions. Here you'll see that for mild hybrid, so the smaller the battery sizes, you have more effective use in terms of well-to-wheel CO2 reductions per kilograms of lithium. But as you increase the battery size, then you have diminishing returns with every kilowatt hours increase of battery size. I'm moving actually quite fast because I think we should spend more time on the panel discussion. So I'll move on to the next slide. So here, what I would like to show here is the opportunity for the use of low carbon fuels. In this particular case, what we have here is the production of synthetic electrofuels, where we have CO2 captured directly from air, so direct air capture, combined with hydrogen, low carbon hydrogen produced from renewable electricity with a carbon intensity of about 150 grams CO2 per kilowatt hours. And we compare that against an electric vehicle running on low carbon electricity, so similar kind of electricity. First point to note is that none of these vehicles are zero emissions on a life cycle basis. However, both technologies can enable near zero, so almost zero emissions on a per kilometers basis. All of this depends on how the electricity is produced or how the low carbon fuels is being produced. In the case of BEV, most of the emissions happen. Throughout the production of the vehicle, but also the electricity production. Whereas in the case of low carbon synthetic electrofuels, the emissions are basically during the vehicle use. However, because the CO2 is being captured from air, so you have a net negative emissions during the production of the fuels. But overall, on the life cycle basis, they are comparable. However, regulations today, with all the zero emissions mandates, or even the fuel economy standards that we have, the greenhouse gas standards that we have today, tend to focus on vehicle use phase which defines zero emissions vehicles such as EVs as being, zero emissions. And because of that, low carbon synthetic fuels do not comply with that definition. However, this is misleading. As you can see here, none of the vehicles are zero emissions. They both are comparable in terms of the overall life cycle emissions. So we need to start thinking about regulations that measure CO2 on an overall life cycle basis. So if you move to my final slide, so here, basically, what this plot shows is the evolution of life cycle thinking in regulations. So the blue grayish line, so that basically shows you the renewable fuels policy. The policy has evolved over time. It started with tailpipe emissions, and then around the year 2000 is when assessments started to take into account of processing emissions, agricultural emissions, and so on. And then around the year 2010 is when we started looking into land use change, direct and indirect land use change. And, they are moving towards a more and more comprehensive and holistic emissions for renewable fuels. However, unfortunately, for the automotive sector, we are still stuck on tailpipe emissions. We've been using greenhouse gas emissions from vehicle exhaust since, even before the year 2000, and it has continued even until today. And this is, this is misleading. And this sort of miscounting of carbon is not conducive when in terms of looking at, standards for mitigating climate change. And with that, final slide. Thank you very much. I hope I've kept within time.
So thank you, Dr. Ram, for enlightening us about life cycle thinking and giving us various objective ways of comparing the electric vehicles, hybrid electric, and other fuels. So now I'm sure that we will have various questions from the audience at the end. So now we will move on to Professor Frank Winter. So he will discuss various futuristic fourth generation fuels and their production methods. Professor Sharma,
good day, Europe from Vienna. It's a pleasure for me to be here, and I hope you can hear me. Yes, so I think it will work. Thank you for the invitation. I'm very happy to be online here.
Yeah, you are audible, but your face is stagnant. It's not. Have you switched off your camera?
Yeah, camera is not working so well. So maybe, yeah, it works for a certain time and maybe connection lost.
All right.
But so thank you. Thank you for your kind invitation, and I'm very happy to be here and to present our work on CO2 to sustainable fuels and chemicals. Thank you for operating the slides. And actual research work in Vienna at our university, TU Wien. Next slide, please. Yes, we have quite recently established a CO2 refinery where the main focus is to use CO2 and to activate it and convert it to high-value products. CO2 should be used as a source from air or similar. So this is the idea, to use CO2 again and develop high-value products. You see on the left side, the area 1, it's the activation of CO2, and to do also in combination with energy storage. So we have thermochemical conversion of CO2, for instance, into syngas, and this CO2 is e.g. from biomass. So it's renewable CO2. And the idea is, as my previous speaker, Dr. Manan mentioned already, to have negative even CO2 effects. However, it's very important, and I fully agree, to have a full holistic view on the CO2 cycle. and carbon cycle. And that's why we have area 3 systems engineering, modeling, and analysis. You see this gray box at the bottom where we have 3 major topics in this area, of course, including a life cycle analysis, economic, ecological, and policy assessment. So this systems engineering part, this area 3, accompanies area 2, which is the conversion of CO2 into fuels, chemical, and even feed products for animal feed, for instance. So it's a combination of thermochemical conversion as well as biochemical conversion, as you see in the areas, focus areas or focus topics 3, 4, 5, 6, and 7. You see, we focus here with synthesis of fine chemicals as well as alcohols. It has already been mentioned, ethanol, butanol, methanol. So different types of alcohol, mixed alcohol, synthesis of mixed alcohols, with a special focus on methanol, with catalytic process, synthesis of methanol. It's topic number 5. We focus also on proteins, nutrients for animal feed, and the synthesis of synthetic natural gas, mainly methane. So this is what we do here in the CO2 refinery, and to see the different routes, conversion routes, study efficiencies, and do a life cycle analysis and economic, ecological, and policy assessment. Next slide, please. Yeah, here you see an overview of the different topics and also the key researchers, the PhDs who work in this area. And you also have this link, the website where you will find more information and updated information in the next years, because it has been recently started this year, and it will be in full speed now, and we are looking forward for new results. And please meet us at the CO2 refinery website we have installed. Next slide, please. Yeah, this is where we focus on power to green methanol synthesis, and we do a detailed analysis of the mass flows, energy flows, balancing, and test virtual different catalysts and guidelines for operation. So the main idea is to convert CO2 with hydrogen into methanol. So hydrogen, of course, is also a key issue for using CO2, because CO2 can be a wonderful carbon source. However, hydrogen is also very important as a hydrogen source we need for e-fuels. And you see here it's CO2 and 3 hydrogen is necessary, 3 moles of hydrogen. So this ratio is like this. So of course, for a good conversion, you have to go a little bit higher than 3. So we have here a hydrogen to CO2 ratio of 3.09. And with a CO2 conversion, of course, with return loops of more than 98%. However, this is the catalyst is very important, and we also test different types of catalyst. In this case, copper zinc was used here, and there are more catalysts showing up in this area, and the idea is to have to minimize preparation of the gas quality. Next slide, please. You see here the concept for power to green methanol. This is in even urban areas where you have also fuel or wood chips, because there are forests. This is Austria is rich in forest and trees. So there's a village and you have forest, and you have a wind park maybe nearby. And to use this renewable energy from the wind, for instance, for the electrolysis, and fast with together with biomass, with the wood chips, the biomass I've mentioned before, to produce methanol, to store it for energy, to store it for transportation, or as a chemical. Next slide, please. Here you have again the full, flow chart here, simplified. You see here in one part, the methanol synthesis is on the right side. You see the methanol synthesis reactor, which is simplified here in this scheme. But you see here the whole flow, which is necessary. So we use here oxy-fuel combustion, using the oxygen from the electrolyzer, actually. So not only the hydrogen is used, but also the oxygen, and to have a high CO2 conversions in the oxy-fuel and the high CO2-rich flue gas from your combustion process. So the wood chips on the left side are fed into the oxy-fuel combustor. Here we have 20 megawatts thermal, and a CO2-rich gas is produced. Excess oxygen you have to reduce, and then you can use the CO2 in the methanol synthesis reactor, producing methanol. You use power, renewable power from the wind park, for instance, for the electrolyzer. So here we have about 16 megawatt electric. And we need some more oxygen. So therefore it's this ASU, air separation unit, to produce the additional oxygen we need. However, what are the feedstock are wood chips, air, and water. The products are methanol mainly, some flue gas as well. Next slide, please. Here you see a case study for 1 year of operation. So annual operating hours are estimated with 8,250 about. And the fuel input is about 50,000 tons of wood chips from the forest close to the village. You have this picture we've seen before. And this gives an annual methanol output of about 17,000 tons per year, with a power equivalent of 177 gigawatt hours per year electric. The annual heat output, which is also, of course, very important for us in Austria for heating purposes, is 100 gigawatt hours per year. So this is about 7,200 households can be supplied in winter time, which is can be quite cold here in Austria. So this is this case study, as you have seen the picture before. Next slide, please. Yeah, this is also a new project. We focus on using CO2 Fischer-Tropsch fuels. We use here CO2 again as a source, and renewable electricity and water. And the basic or the main features are here this combination of solid oxide electrolyzer cell of a SOEC in co-mode. So it's CO2 is already fed into the co-SOEC in combination with the Fischer-Tropsch process. So you see at the right bottom, you see the Fischer-Tropsch reactor. It operates at high pressures, favorable, and you produce Fischer-Tropsch diesel, which should be our main focus, is the main focus of this project, as well as naphtha and waxes. And this is for e-fuels and sustainable fuels here. A demo plant is what we will do in the next step. Of course, you can optimize for energy supply, and you see it as coupling of electrolysis and Fischer-Tropsch. Next slide, please. Yeah, the performance targets for this demo plant are 1 megawatt, 1 megawatt electric renewable. This coupling I've mentioned at high efficiency, 55%, and the products about estimated simulated 160,000 liters Fischer-Tropsch diesel, 150,000 liter waxes and 150,000 liters, so the same amount of naphtha per year. And of course, these are also valuable products which can be further used. There's also the homepage you can visit. It's viva.at, and you see this innovation liquid energy project we work on. Next slide, please. So this is the end of my presentation, and I look forward for discussion in the panel discussion. Thank you very much.
So thank you, Professor Winter, for highlighting the conversion of CO2 into various attractive fuels like methanol and CO2, which are top fuels. So now we will move on to Professor Leonid. So he will talk about futuristic fuels, hydrogen, and solving the issue of hydrogen utilization, hydrogen storage by its storage and onboard generation in the form of methanol. I will request Professor Sharma to introduce Professor Leonid.
Yeah, thank you, Dr. Atul. Professor Leonid is the director of Technion Internal Combustion Engines Laboratory at the Department of Mechanical Engineering. His research interests are focused on energy conversion in propulsion systems, advanced thermodynamic cycles, alternative fuels, thermochemical recuperations, combustion and emission control. Dr. Leonid serves as an associate editor of the SAE International Journal of Engines and the editorial board member of several journals. Dr. Leonid is a recipient of SAE Forest R. McFred Award. He was elected as SAE Fellow in 2016 and SAE Top Contributor in 2019. He is the founding chairman of 3 international conferences, served on organizing committee of multiple conferences, and has 100 publications in journals and conference proceedings. I welcome Professor Leonid to kindly give his presentation. Professor Leonid, can you unmute your mic? You are not audible. Professor Leonid?
Do you hear me, please?
Yes, sir. I confirm.
Okay. So you will control my presentation, and I will start. So first of all, thank you very much to the organizers, Professor Agarwal, Professor Dhal, and all the organizers that invite me to take a part in this important conference. And my warm wishes to everybody from the Technion, the oldest University of Israel and home for 3 Nobel laureates, which is located in the sunny city of Haifa. In better situation, I will warmly invite you to join the conferences that we organize. Please, next slide. No, the next slide, please. Yes, I would like to express my greetings and thanks to the previous speakers, Dr. Aman and Professor Winter, because they make a wonderful introduction to what I'm going to talk. As regarding the electric vehicle, you already heard that it is not really zero emission option. Life cycle analysis is something which is extremely important to understand the real situation. And I will only add a few words to what was talking already by the previous panelists. Take a look, please. Some of advocates of electric vehicles talk that they truly zero emission in driving, which is not correct because they pollute the most harmful emission particles on the same amounts as a motor vehicle. This is the first comment. The second important comment, which in my opinion must be taken into account in life cycle analysis, is not only greenhouse emissions, as already was said, and not only pollutant emissions, but a different ecologic burden, which is critical in battery production, such as soil acidification and water eutrophication, which could bring the humanity to much more serious crisis as compared to the climate change. Next slide, please. And if we take this into account, so alternative fuels like hydrogen, which is a truly carbon-free fuel, could be a wonderful alternative. Indeed, hydrogen is featured by extremely wide flammability limits, extremely high burning velocity. Only to put you synchronized, the burning velocity, for example, of hydrogen is more than 7 times higher compared to that of gasoline, which brings the combustion of hydrogen much closer to the theoretical Otto cycle, which is the most efficient one. But if we talk about hydrogen vehicles with a need to fuel by hydrogen, there are major obstacles we are facing with. First of one is the non-availability of fueling infrastructure. And the second, which is not less serious, is hydrogen on board storage. To understand this, please take a look only on this number. Hydrogen boils only at 20 Kelvin, minus 253 Celsius. This says everything. Please, next slide. And in such a case, the onboard production of hydrogen, instead of keeping it on board, could be a wonderful alternative. And this can be done by waste heat recovery through the process which is called thermochemical recuperation. What it means that we use the heat of exhaust gas or other heat source. We fuel the platform by a liquid fuel, for example, as Professor Winter reported us, by methanol, which is the excellent electrofuel. And the methanol can be reformed with use of waste heat through endothermic reaction, but exactly the opposite reaction as Professor Winter showed you already. So we have methanol, we add some water, we add some heat, and what we receive 3 moles of hydrogen and 1 mole of CO2. So this shows you how our world is the circling one. Professor Winter reported you how to use CO2 and hydrogen to receive methanol, and I talking to you how to use this methanol to produce in opposite manner the hydrogen and to combust the hydrogen. And please, next slide. This I will make very, very quick because we heard already why methanol is so good fuel. I only will add that one of the important benefits of methanol as a fuel for the reforming, for thermochemical recuperation, that it can be reformed at very low temperature, approximately 250, probably 300 Celsius only. This allows us to utilize perfectly the exhaust gas of engine. Next slide, please. This is what we heard already from the previous speakers. Methanol is the excellent electrofuels. Next slide, please. And now I will show you very briefly, because of the shortage in time, about possible reforming techniques. Each of techniques could be a best solution for different primary fuels. For example, if we talk about steam reforming, you see here the example. When we use the liquid fuel and water, no hydrogen, we produce a lot of hydrogen. This is this technique well suited for alcohols, for example. Next slide, please. Autothermal reforming is well suited for the reforming of gasoline or methane because it uses some oxygen to provide an additional heat. Next slide. Exhaust gas reforming is also well suited for heavy fuels reforming, and it uses one more reaction with CO2, so-called dry reforming. And in such a case, exhaust gas simply added into the reaction. Next slide, please. When it is problematic to use an external reforming, one cylinder of engine can be devoted and combusted with a rich mixture to produce some hydrogen in a partial oxidation reforming, and the products from this one dedicated cylinder can be returned to the three remaining cylinders to fill them with the hydrogen. In such a case, no additional reforming, but of course the advantages in terms of efficiency and pollutant reduction will be lower. Next slide, please. And this is the revolutionary technology that we have developed in the Technion. We call it high pressure thermochemical recuperation. Please make an additional click. One click more, thank you. And in such a case, you see, anyhow, that this is the only technology that allows going to gentlemen. Okay, this was the only technology that allowed us going to combust hydrogen as a standalone fuel. And I will finish with one step more, so-called hybrid fuel cell thermochemical recuperation internal combustion engine cycle. And you may see we combine here fuel cell, engine, and thermochemical recuperation, and take a look on this number. We can achieve the efficiency numbers above 70%, which is the efficiency of electric vehicle. Next slide, please. And this is the last one. And the conclusion, we can use thermochemical recuperation to produce hydrogen on board. We can achieve a great advantages in terms of efficiency, between 20 to 30% improvement, dramatic reduction in pollutant emissions, and we also talk about 70% efficiency if we combine this cycle with a fuel cell. Thank you very much. It would be great if you will unmute yourself.
Now I will request our last speaker, Dr. Anirudh Gautam, to give his opening remarks about renewable fuels utilization status in India in transport sector.
Yeah, before Professor Anirudh starts his presentation, I'll be quickly giving a brief about him. Dr. Anirudh Gautam is the Principal Executive Director at Research, Design and Standards Organization. Dr. Gautam is a mechanical and electrical engineer from prestigious SCRA scheme of Indian Railways. He has served initial years on Indian Railways in maintenance on carriage and wagon maintenance and operation, steam engines, operation and maintenance of diesel locomotives, and train crew management in the challenging eastern sector of Indian Railways. He is credited with the design of first motor load feature on the export locomotive and was instrumental in building the first indigenous EMD locomotive in India at DLW. His thesis work at IIT Kanpur on biodiesels led to B10 blends on all locomotives of Indian Railways. He has been working on researching and developing alternative advanced propulsion systems. His main areas of interest are energy production devices, fuel cells, hybrid powertrains, and sustainable motive power systems. So I welcome Dr. Anirudh Gautam to give his talk.
Thank you. Am I audible? Okay. Hello.
मोबाइल है क्या तुम्हें?
हाँ मोबाइल. Good afternoon, ladies and gentlemen. Professor Agarwal, good afternoon to you. All my friends here. So, I'll be talking about what is the policy of Government of India on renewable fuels. And there are a lot of things which the Government of India is doing. And some of the projects are in advanced stage, and some are starting to happen. So, as you know that there is a methanol mission which was announced by the NITI Aayog under the chairmanship of Professor Dr. V.K. Sagar sir. And this methanol mission has been going on since a very long time. So this is basically converting the existing IC engines on gasoline and diesel to run on methanol, oblique DLE. Then there's a hydrogen mission which has been recently announced by the NITI Aayog and Ministry of New and Renewable Energy. Basically green hydrogen, which is through renewable energy. Then, in addition to that, there's an e-mobility mission where India plans to manufacture and use e-vehicles, maybe pure e-vehicles or hybrid. Then there's a solar mission, which is photovoltaic and concentrated solar power missions there. There's a wind power mission. Then there's a biomass to syngas conversion project, a pretty large project. Municipal solid waste to syngas conversion, and next gen battery development. So there's a whole, you can say, list of projects and missions which have been announced by the Government of India from time to time. And if I remember earlier, there was a biodiesel mission also, which went on for quite a long time. And of course, now it is not there at all. But I'm sure that this is happening because Indian Railways switched over to B10 based on our work in IIT Kanpur. And now all the diesel locomotives of Indian Railways are using 10% biodiesel in their blends. So there is something which is being advertised and there is something which is happening. I am sure many of you would not be knowing that diesel locomotives of Indian Railways are running at 10% better. All of them are running. So we are procuring, and that has basically accelerated the biodiesel industry also in India. So people are converting waste vegetable oils to biodiesel, and a whole chain of logistics which has built up around this. So, as you know that railway stopped manufacturing of diesel locomotives recently. We had two production units, one in Banaras and the other at Patiala, where we were manufacturing diesel locomotives. But because the government of India doesn't want to go for petroleum fuels, so both the production units they stopped manufacturing diesel locomotives. And so that has been a kind of a setback to the IC Indian industry in India and also abroad. Similar kind of approaches are being used in US or in Europe or in not in China. China is not looking at it like that. Japan, of course, doesn't have much diesel. So, and also not in Australia, not in South Africa, which are quite diesel intensive. I'm talking about the locomotive sector, not the road sector. So, if you compare the e-mobility versus biofuels, so you'll find that the e-mobility there's a growth of almost 260% year over year in the EV sales. You can see scooters or cars. Maybe in India it is slightly late in coming, but it is happening, especially in Europe. Whereas in biofuels, if you compare the Europe one, I'm sharing the Europe figures, but Indian figures are not there. We don't have the figures. It's almost 10% increase. It was last year in biofuel vehicles. So there's a very big gap. 260% versus 10%, a very big gap. And we can see the ill effects of that. People are beginning to believe that e-vehicle or e-mobility or battery is the answer for mobility, or electricity is the answer for mobility. So let me tell you, we did a very, there was a comparison when I was in IT Kanpur, I did a comparison between the diesel, electric, methanol, and so for the locomotive, for the railway sector. And the results were really shocking because although we are running the electric locomotives, but the power generation is all from the coal-fired power plants. Although we are saying that we will switch over to 100% renewable, but that's a distant dream. It may happen, it may not happen, because that is another study. So saying that we will replace all of electricity with renewable like solar or wind is a very far-fetched idea. So because these are intermittent sources of energy, and even if you put, let's say, 500 gigawatts of power from these, the actual delivery to the system will be 5%, 10%. So it is not as if that you are going to get 500 gigawatts. So in India, of course, this electric plug-in vehicles for HEVs or EVs are also picking up, and all the sales are picking up, and all these manufacturers, automotive manufacturers, they have announced some electric vehicles some way or the other. So in Europe and in the rest of the world, advanced world, almost it is 10 to 15% are electric vehicles, and about 4 to 5% with biofuels, fuel vehicles. Fill up time of battery vehicles, of course, is like 4 to 6 hours, whereas biofuels can be filled in the same time as current gasoline, that is 5 minutes. Driving range also with electric vehicles would be 100 to 300 kilometers, and of course the biofuels do not have any problem of driving range. So, yeah, just finish.
We can take further discussion.
Yeah, this is my last one. Just finish. So what I'm saying is that we have to take this debate to the policymakers because all over the world it is accepted that simply having the EV or electric locomotive will not solve the problem. We have to have a basket of fuels, basket of energy sources in order to have a reliable system. And in case the renewable the targets are way far ahead. So we have to take a conscious decisions, and take it to the policymakers. So just last concluding remark. In Germany, they did a recent study, 2020 study, a diesel car fueled with IME, that is rapeseed methyl ester, so biodiesel, and had lower climatic effect than a comparable battery electric vehicle. And this is one of the reasons Germany is not going as immediate source of e-cars. Even Japan, for that example, which is almost 100% electrified as far as it is concerned. So we need a basket of fuels. As was advocated by one of the papers by Professor Albert of University of Adelaide in 2010, we need a basket of energy sources and fuels. Thank you.
So, thank you, Mr. Gaurav. So, I hope the opening remarks by our panelists might have generated a lot of questions. So, if mic works, we will allow you to announce your name and ask the questions. If not, then you can share your written questions and we will ask the panelists on your behalf. So first preference will be to physical participants, then we will move to online.
Yeah, I have good afternoon, Avinash Agarwal from IIT Kanpur. I have a couple of questions. One is to Dr. Amir Manan. So, Amir, what do you think in the absence of metals? What will be the best solution for transport? Because now, BEV is talked about all over the world. Do you think there is enough material available in the whole world if we electrify entire transport of the entire world? Do you think that's a possibility from material feasibility point of view? And my next question is to Professor Franz Winter. So, what are the major challenges in producing methanol from low-value biomass? Because in India, producing methanol from low-value biomass is very important. And will it be viable from energy point of view? That means how much energy is really invested in production versus what comes out. Thank you.
Professor Winter.
First one.
Professor Ahmed. Thank you, Anil.
Yes, hi. So do I answer the question now?
Yes. Yes.
Okay. Okay, so I guess this is a really important question. Do we have enough critical metals to electrify all of the transport sectors worldwide? So not just India. Now, today, when we look at the production of metals, they are highly concentrated in several different countries. Now, if India alone goes ahead with its electrification plan, based on some of the analysis that we've done, India will probably require about 10% of projected worldwide productions by 2030. Now, of course, this is based on current means of production, yeah? Looking at current means of production, which is basically terrestrial, surface mining. Yes, we don't have enough to electrify all of passenger transport, including heavy-duty transport sectors. But the next frontiers in battery production or critical metals production is now basically looking at deep sea mining. So this is moving away from surface mining and going into ocean mining. Now, some of the estimates that have been done shows that there is significant amounts of materials in the deep seas. But now we have a different problem. Now, the deep seas is basically a very sensitive ecosystem. So we need to have some sort of mechanism to ensure that the materials that we produce are sustainable. So the question is no longer, do we have enough materials for battery productions to electrify all of the transport sectors worldwide? But the question should be, do we have enough sustainable battery materials to electrify sustainably all of the transport sectors worldwide? And the answer to that is, I personally, I don't think we have, because we don't have regulations in place to ensure that only sustainably produced materials are allowed in the use of electric vehicles. And I think this is one of the things that we need. So biofuels industry, they've gone through this phase. They started with this question of, do we have enough land mass available? Do we have enough biomass available? And then it evolved into a discussion around, do we have enough sustainable biomass available? So I think, now the biofuel industry, they have regulations that define the minimum requirements for sustainable biofuels. I think at some point we need to move into this discussion, to define the minimum acceptable definition of sustainable batteries. I think this is the next step.
Professor Venkat? Yeah, Professor Venkat.
Yes. Okay. So thank you very much also, Professor Avinash Agarwal, for this very good question. Low value biomass is very important, and we have to use it. The major points are here for methanol production are the catalyst. The catalyst at the time being is quite sensitive to impurities, for instance, for sulfur and other species. So this is a very important research point to develop new catalysts which are more robust to certain impurities like sulfur. And we also focus already in cooperation with our colleagues from physical chemistry. The new catalysts are showing up, so like molybdenum sulfide, which are more robust. So this is just one point to further improve and use low value biomass. And of course, if you have a catalyst with the importance of having very poor gases and very good purified gases, I would say. Like this, you can, instead of the catalyst, you can clean the gas, but this needs a lot of attention and is also plays a role for the techno-economic analysis of the whole process. The same is also true for solid oxygen electrolyzers and so far to the gas cleaning. So gas cleaning is a very important part of the whole process. And this is what I want to point out, to use low value biomass, which we do also in gasification, for instance, to use waste biomass. Also in pulp and paper industry, we use low grades. And so this is a very important issue. The catalyst is one key figure, and to go for more robust catalysts or for gas cleaning for the time being. So both strategies are important, I think, for this aspect. I hope this could answer.
Yeah, so thank you, Professor Winter. So
thank
now
you.
there is one question for Professor Leoni. So it is being asked, so can you explain what is the advantage of burning of hydrogen over direct burning of methanol in the engine?
I'm sorry, this question to me is I do not hear the question good. able to understand if you are writing to the Q&A to be good. We try to answer.
Excuse me, sir, your voice is not clear. Can you please switch off your camera so that your voice will be clear?
I'm sorry.
Okay. Sir, I have switched off your camera. I think you can proceed.
I may try to switch off my camera, but the quality of sound is not so good.
Sir, okay, you can answer. Hello, Professor?
Yes, I'm here, but I said that I cannot hear the question, and for this reason, I don't know what I should answer. I'm sorry for that.
We'll repeat the question once again.
So, advantage of burning hydrogen over direct burning of methanol. So, why it is advantageous to first reformate, then burn hydrogen, rather than direct burning of methanol? So, Professor Leonie, okay, Professor Leonie, we are typing the question, and meantime, we can go ahead. So, there is a question for Dr. Anjit Gautam by Professor Raja Banerjee. So, he has asked, so can you briefly summarize what were the initial issues for utilization of hydrogen?
Hello. So, I think you're talking about hydrogen. So, hydrogen, the target is that Ministry of Railways has taken up a project on fuel cell multiple electric unit, and that project is going to come up. So we are going to convert one diesel multiple units, remove the engines, diesel engines, and put fuel cells and associated electrics and electronics. So this is one project, but if you would have noticed in recently the papers, there was an announcement by the ministry saying that this is going to be taken up as a very mega project, converting all our DMOs and maybe manufacturing more with fuel cell, hydrogen fueled fuel cells. So that's the situation as far as the vehicles is concerned. Then there is a move to go for hydrogen in the workshops. So that is not pure hydrogen, that will be hydrogen, methane mixed together. So where we are using currently like furnace oil in our workshops, so that also that work is good, that project is going on. So these are the two areas.
Professor, you have put the question in the Q&A tab.
Okay, I received now the question about advantage of methanol reforming and burning the hydrogen over direct burning of methanol in engines. So the advantage of burning the hydrogen is great. First, when we burn hydrogen, it burns 7.5 times quicker as compared to gasoline, and if I remember correctly, approximately 6.5 times quicker compared to methanol. This is an important advantage in terms of efficiency. The second advantage of burning hydrogen over methanol is that burning methanol brings to production of aldehydes, which are extremely harmful. When you burn hydrogen, aldehydes are not forming. And additional and last advantage of burning hydrogen, which is produced by methanol reforming, that you utilize the waste heat. So you receive in such a way an additional advantage in terms of efficiency. Hope I answered this question.
Hello, I'm Dr. Partha from IITR. I'm proceeding to IIT. Hello, yeah. I'm Dr. Partha from CSIR IITR. I was listening to you, I'm very curious to know about what is the relationship between the CP number, octane number, with the emission you have shown? Like, does they anywhere relevant to your SOx, NOx emission? Because it's related to all the burning rates, right?
Mike.
See, these two numbers basically tell you how good your fuel is when it comes to performance and emissions. What we try to do is to, make the fuel in such a way that it doesn't allow the fueling element to stay for a longer time in the combustion loop. So once you reduce the residence time of fueling elements in the engine cylinder, then what happens is this time to form NOx or HOX also reduces, and they don't get enough time to be formed. So targeting a quality cetane and octane rating fuel will be one of the potential alternatives to reduce the ignition delay in the engine cylinder. So these two things are basically contributing towards most of the emission. So what we try to achieve is that not losing too much properties of biodiesel, and also having at the same time higher cetane rating. So these two things can make your fuel even more applicable to the realistic size engines. Have I answered your question? Or?
Yeah, that way we can predictively we can make a fuel blend.
Right. That's the procedure we are following over the last 3 years. We started with a small engine, tested the fuels there. Since the blend which you just saw, they are predicted on our hands before. So we have been granted this patent. So now what we want to see is when we scale up the engine side. So what happens with all these properties? Do we get the same result or not? So what we found in our initial series of tests is that the results are more or less in the same way like in small scale engines. So now we have a better level of confidence to say that yes, this blends can be an alternative fuel for the existing vehicles also.
Thank you.
You're welcome.
Yeah, thank you, Professor Mishra. So now we are going to start the contemporary papers, and we'll be calling.
How many minutes final? 1 minute.
Okay. So to conclude this session of the talks by the presentations given by various panelists. So as you all know, Professor K.V. Mishra talked about the effect of engine size on the emissions and observe that the size effect is not much going to affect in terms of the emissions. Then Professor Sharma talked about the production aspects of biodiesel, and wherein he discussed the production viability of biodiesels. Then Professor Manan talked about life cycle analysis of various fuels and how they are going to affect. It's not only the drivetrain which is going to affect their business. Professor Winter talked about CO2 requirements and production of various fourth generation fuels. Then we had a very interesting talk by Professor Leone. He talked about hydrogen utilization in IC engines as a future transport fuel. And we all know hydrogen seems to be the future trend. If you see the hydrogen by carbon ratio of the upcoming fuels, this is going to increase. So starting from the liquid fuels which are very low H/C, then we are moving towards the gaseous fuels. So H/C, if we extrapolate, it's going to tend towards infinite, which means hydrogen is going to be the future fuel. And towards and we had the presentation by Professor Anil Gautam. He talked about the possibility of using fuel cell in replacing diesel locomotives with hydrogen fuel cells. So the presentation had an activity, and before I ask the continuing papers to be started, I'll ask Dr. Atul to give his remarks also.
So we can use this time, but I will brief concluding remark by our panelists. So within 1 minute, how they see the future of transport fuels. So maybe starting with our first speaker. So but time we have to be very precise, within 1 minute.
What I see as a future is a collective list of all the fuels that can become an alternative to the existing fossil fuels. Now, coming to how we will be able to produce these fuels in the required quantities. This is a major challenge for the developing countries like India. But at the same time, we are quite optimistic that this will be made by all-round effort by the different stakeholders.
So Dr. Amir, so how you see the transport fuel future?
I think, the way I see it is that we will have a diverse solution for the different transport sectors, and different countries will have different pathways that they will have to take depending on the technologies available, resources available, and their current status of development. So you'll see a mix of different technologies worldwide and different transport sectors.
So Professor Winter, so
I fully agree with Dr. Abdul Manan. I also think there will be a diverse system and a mix of fuels and also electrical vehicles. So this is what I expect. Thank you.
Thank you, Professor Winter. So Dr. Gautam.
Thank you, Professor. What I can see, mixture of different energy sources, especially for heavy vehicles like railway, we have one electrification option, but we have to think of hydrogen or ethanol fuel, also fuel cells, and for lesser light vehicles, I think it's again going to be a mixture, and so we have to plan for everything together. But I definitely see drastic reduction in petroleum fuels in the coming years. Thank you.
So after the views of Professor Subrayani, we will move to the Benoit. Yeah, Professor Benoit.
Yeah, my opinion is exactly the same as that of Dr. Abdul Manan and Professor Winter. There is no silver bullet solution. The decision makers should understand that there is no only ultimate solution, and that electric propulsion is not the one. And as already said, depending on the application, there will be technologies that will be dominant, but in general, all the technologies, both electric propulsion and internal combustion engine-based propulsion, will be in foreseen future. And what is important to add, that the alternative sustainable fuels will enter the market, and they will gradually replace the today's used fossil fuels. Thank you.
So thank you, Professor Benoit. So now we will move to the contributed papers. So here the strategy is to finish the presentation within 3 minutes, and then one or at most 2 questions will be asked to each presenter. So here we are going to be very strict with timeline to conclude the session at 3:30. And we have 7 contributed papers in this session, and I hope all the evaluators, they have evaluation sheets with them. So first presenter is Vikram.
Just a reminder to all the speakers who are on the virtual platform, we have sent you email with the Word documents that will be used for scoring. So please use them to score, and there are instructions in the mail about how you are going to send the result. So please do that after the session. Thank you.
Good afternoon to all teachers. Today I am going to present about the essential characteristics of the methanol condensate reagent. Here you know that the emissions from the engines are diesel engines are not good for the environment, so there is substitute for the application of the alternative fuel. So methanol is one of them that can be used for the fuel for the IC engines. And several methanol can be produced by the various renewable resources, and such as coal, biomass, syngas, and CO2 from the atmosphere, which can be converted to some specific reaction to methanol, which can be used in the RC engines, in the SI and CI engines, in both, and that it can be used in the dual fuel technology, and the minimal content oxygen, which is good for the conversion, and then methanol can reduce simultaneously NOx and soot. We have for the application of methanol in genset engine, we modified that existing issue change to some open, like open issue which can be programmable, and then we modified the inlet manifold, and we used that separate methanol injection in port, and then we have also used that turbocharged air to heat the methanol injected in the inlet manifold, and which can these methanol application in that engines can reduce the emissions from such as that NOx and PO, and SCNC will be enhanced by using that methanol, and that the particulate from emission from that diesel engine in case of dual fuel technology were much lower than the conventional diesel engine, and that particle size, larger particle size engine were also higher in that commercial diesel engine as compared to that dual fuel engines as we modified in gas engine. And that we have also measured that TPM, PPM, the counter main diameter, which is lower for that methanol fuel engine, all the inserts. And here we have concluded for that all the in terms of inserts, as you can see that within the dual fuel engine, PPM, and NOx will reduce much as compared to the conventional diesel engines. And that 30% and the 50% methanol application in that in engine is much better than as compared to 80%, and that higher percentage of methanol will not complete, combust completely. So we have observed that the 50% methanol replacement is much better than the other percentage of methanol. Thank you.
Thank you, Vikram. Any question for Vikram? Yes.
So you talked about how much percentage of methanol in your engine?
We have replaced that maximum 80%.
Maximum 80%. Yeah. What happens to the performance?
Performance in 80% is lower as compared to conventional diesel.
Should it be lower for all percentage of blends?
No, for it's up to 50%. The performance is much higher. Near about at 30%, it's near about 8% higher than the
justification to that.
Yeah.
Can you give me a slight justification for that?
Okay.
Can you give the justification?
As a lower percentage of methanol, its oxygen content is help to better combustion, and also the higher enthalpy of methanol at high percent lower the combustion temperature, so the complete combustion of the methanol will not take place at the higher percent.
Okay.
So, thank you.
Hello. Yes. So my title of the presentation is identification of suitable octane and enhancer fueling for two-wheeler segment. So as we know, the government is focusing on two verticals. One is ethanol blending program and other is ethanol blending program. So the speakers already talked about the advantage of both fuels. So I am just saying about the aim of the study. The aim of the study is suitable vertical suitable fuel for the two-wheeler market. M15 or A15. So, in the to assess the suitability of the fuel, the vehicle was tested. The vehicle used was a two-wheeler 125cc, and the fuel used was the G100, M15 and E15. For the M15, as per the specification of IOCL, 3% isopropyl alcohol was used to avoid the fuel separation, and the entire vehicle was tested on the chassis dynamometer. That is the setup that used in the wheels for testing the vehicle to meet the vehicle norms. And the gear position was followed as per the recommendation of the OEM, and the road load simulation as well as the wide open super condition was tested on this setup. This is a chassis dynamometer. So I'm coming to the results of the road load testing. So from the M15 and E15, due to the overloading, we observed that due to the overloading condition, the CO was reduced. As well as the CO2 was also reduced. The question comes that why inert oxygen is not able to enhance the CO2 to CO2 reaction, because in RLS testing the O2 was coming out as a tailpipe. So basically we are saying that inert oxygen sometimes due to the throttling process it is not participating in the combustion and it is coming at the tailpipe. So this was the main conclusion from the RLS testing, and the NO was reduced for the M15 and E15 both. And regarding the FC, LC, the methanol and ethanol both have a higher energy of vaporization. So after it reaches some speed, then it behaves as per the gasoline, and then it produces hydrocarbon less than the gasoline. And regarding the power at wheels, we observe that methanol, N15 and E15 both are giving the power at wheels higher than the gasoline. But the max power at wheels was higher in case of the M15 compared to the G100 as well as the E15. And the maximum speed was for the M15 as well as the E15, it was comparable to the G100. Now coming to the another WOT testing. So in the WOT testing, the CO was reduced as well as this CO was reduced, and in this condition CO2 was increased. So CO2 conversion was enhanced in this WOT testing, and in the NO was increased in case of G100 as well as the M15 as well as the E15. Now coming to the decisive diagram. So in decisive diagram, we can see that for the max power at wheels was higher as well as the max speed was higher. So M15 is found as a suitable fuel compared to the E15. This is the study based on the sustainability point of view. Regarding economic as well as the scalability point of view, M15 is giving advantages over the E15. Thank you.
Quite interesting work.
Could you please make some comments on the effect of dilution on different engine components when you blend higher proportion of methanol and ethanol?
Dilution in the sense.
What happens with the combustion? Because it's not about running the engine for half an hour, it's about running the engine for a few years.
Yes. So it is a study for the test the vehicle performance and emission. And regarding dilution, we have to do the field trial and everything, but this is not concluded in this investigation.
Could you please think of how we can assess this dilution effect inside the engine cylinder?
Dilution effect.
You're talking about durability or dilution?
I don't understand
It's about the water vapor that forms. So if you water condensation combustion.
Okay, so in methanol, M15 the dilution H2O is higher. So actually the H2O formation is coming, but H2O is coming from the silence down. So basically, if dilution is coming, H2O is coming, then it is good for any fuel. Either is a M15 one, because we need that H2O is coming.
Okay, thank you.
Hello everyone, my name is Krishna. Particular characterization of cathode through medium loop is artificial. Environmental pollution from automobiles have become a global concern. Also, depletion of fossil fuel is another issue. Therefore, it is essential to explore alternative fuels which could lower harmful emissions and fulfill energy demand. Alcohols are most appropriate alternative fuels. If necessary, vary in alcohol blends such as methanol gasoline, ethanol gasoline, butanol gasoline, very investigated for EM characteristics. Due to time constraint, I am only presenting results of physical characterization of EM. Vertical size number distribution for all these flows. The distribution is bimodal. It was found that concentration of particles increased up to medium load. However, no further increment was observed at high load. At all engine loads, gasoline alcohol blend indicated relatively lower particulate than baseline gasoline. This is due to presence of fuel bond oxygen in case of blends. Enhanced alcoholized fuel air mixture, superior combustion and rapid soot oxidation, lower particulate emission. Lowest particulate number concentration showed by GM10 at lower engine load. However, GM10 showed lowest particulate number at medium to high load. Figure 4 comparison of NC, nanoparticle, NMP, nucleation mode particle, and aeration mode particles for all tested. It was found that the gasoline on cold plane exhibited lower NMP, AMP than gasoline. Among different planes, GB10 fuel engine exhibited somewhat higher particulates. AMP contribution was almost same for all gasoline on cold plane. Another figure shows variation of ppm and CMP for all days fuel. It was found that gasoline on cold plane emitted somewhat lower ppm than gasoline at all engine load. Somewhat reduced concentration of bigger particle was major reason for such trend. ppm from GM10 fuel engine was somewhat lower than other days fuel. This is due to highest percentage of fuel-bound oxygen, leading to soot oxidation. CMP showed weaker effects on engine load variation. GE10 showed minor variation with engine load. Except GE10, other gasoline alcohol plane showed lower CMP at all engine load. So physical characterization showed lower number concentration for gasoline alcohol plane amongst different planes. GM10 showed relatively lower particle number concentration and GB10 showed highest particle number concentration. Thank you.
Utkarsh, can you comment why we observe two peaks in the particulate number addition curves? What is the possible reason?
Actually, sir, this is the biological distribution which are mostly observed in the SI engine. So that means that means that the number distribution increase in the fine local and other decreases and other start increasing in the most local particulate. That's a very special curve we can observe.
So any reason, like for any fuel, what are the reasons that peak happens at certain points?
So this is the transition point from the nanoparticle to the NMP, and second one is observed from NMP to AMP.
Thank you.
Thank you, sir.
Good afternoon, everyone. So, continuing our discussion for the fuels for transport, sustainable transport, I'm going to discuss the detailed engine characterization study for influence of diethyl ether addition in heavy-duty tractor engines. So, discussing the background and motivation, so we can see that the 2/3 of our oil, that is crude oil, is used for the transportation purpose, which actually provides 25% of the world's power, and in return it produces 10% of the world's greenhouse gas emissions. However, increasing number of vehicles leads to the growing pollution, and also we have limited crude reserves, so there is a need for the utilization of alternate fuels. Therefore, the IC engine community have always focused on reduction in fuel consumption and engine emissions. So, we are going to discuss here the diethyl ether as an alternative fuel. So, this is considered a best fuel for the CI engine. So, here I have listed the properties of diesel and diethyl ether. So, you can see here that there are some properties which are basically very different among these. So, the latent heat of evaporation, which is very high in diethyl ether, its CK number is very high, which is very beneficial for diesel engine, and also it has oxygen content, which helps in the emissions. So these are some favorable properties. That's why it is a good fuel to be used in the CI engine. So this, the methodology of our experiment is that we are investigating two fuel ratios. That is the diethyl ether, which is 15% and 13% in the diesel engine. And we are using here heavy-duty diesel engine with a mechanical fuel injection system. And we are actually analyzing the performance of the engine in terms of combustion characteristics, performance characteristics, and diluted emission and particulate emission characteristics. So here it can be seen this from the schematic, the different components. So discussing the results, if we see the combustion characteristics, we can see that increasing the addition fraction of the diethyl ether in diesel, it actually retarded the combustion. So actually it is, however, not so obvious because diethyl ether has a higher cetane number. So it should lead to shorter emission delay. But we can see that it is leading to the retardation of combustion. So here it can be just that because of high latent speed of vaporization of diethyl ether, it is actually leading to the cooling effect, and hence the combustion is retarding. However, this effect is reduced in case of higher load of emission, and it is actually resembling to baseline. So combustion wise, we can see that at lower it is slightly different, but higher load it is actually similar to that of diesel engine. And regarding the brake thermal efficiency, we can see that it is actually comparable to that of baseline diesel performance, and actually higher at some higher load. So performance wise also diethyl ether is better, both 15% and 30%. And if we see the regulated emissions, so you can see that the carbon monoxide and the hydrocarbon emissions are both comparable for diesel and diethyl ether. However, we can see that we have a significant advantage on NOx emissions. So NOx emissions are considerably reduced for diethyl ether, that is 30%, which can be due to the cooling effect of diethyl ether. And if we see last particulate emissions, so we can see that the particulate emissions are also lower for diethyl ether, 30%. So both the nanoparticles, which are smaller size particles, and the accumulation mode particles, which are having size greater than 100 nanometer. So both we have seen reduction in the particulate characterization. So discussing the conclusion, we are actually analyzing the 4 parameters: the Rmax, the combustion rate, the NOx, and the DPM, that is the emissions, and the brake specific energy consumption, that is the performance. So we can see that the performance-wise, all the 3 fuels are behaving same. And however, we can see the advantage on the NOx side and the smoke. So we can actually suggest that the diethyl ether blending 30% in the diesel can lead to good performance in emissions. Thank you.
So good presentation, thank you. What was the motivation for you to restrict yourself to 30% only? Why don't you go ahead more than that 30%?
Yes, and actually we have tried some experiments going to around 45%. Okay. But we saw the problem of vapor locking in the fuel supply line, induction line. Okay. So because it has lower vapor pressure, so chances of vapor formation is very predominant in case of higher acidification. 45%. So 30% is actually performing well in all load conditions. That's all.
Okay, thank you.
Thank you.
You can actually clap for the speakers.
Hello. Very good afternoon, sir. Today my topic of presentation is utilization of dimethyl ether as a low carbon fuel in single cylinder genset engine. So, objective of the study was to analyze the various engine exhaust emission of DM10 engine and compare the emissions of DME with the baseline diesel fuel. So, why we use DME? DME is very ultra clean energy source. So, main problem with diesel is higher PM and soot and NOx emissions. So we can minimize the NOx and PM emissions simultaneously with the use of DME. Because DME has the absence of direct C2C bond, so it minimizes the formation of direct CC bond, which is the precursor of the soot formation. And it also reduces the NOx emissions. And high S4 can be utilized for the DME production. But DME has a certain limitations like low viscosity, less lubricating characteristics. But we can modify the existing fuel injection system to implement the DME into the system. So we can clearly see that in the property section that C10 number of the DME is significantly higher than the diesel, and the latent degree of vaporization is also significantly higher. So how we implemented DME into the engine? So that's the part of methodology. So first we modify the existing diesel fuel injection system. We add the lubricity attitude to the DME because DME has very less self-lubricating characteristics. And then we install the intermediate heat pump to compensate for the higher compressibility of the DME. Otherwise, high pressure pump would not generate adequate amount of pressure. And then we analyze the STCO, CO2 and NOx emissions and compare it with the baseline here. So this is the basic schematic of the single cylinder genset engine, where we can clearly see the modified fuel injection system and other components. These are the real images where you can see the modified fuel injection system and the DM10 Kirloskar genset engine, where we fire the engine on DME. So this is the arrangement for the dosing of the lubricant. So these are the results where we can clearly see the significantly less NOx and CO2 emissions in the case of DME for the entire load range. But higher SC and CO emissions at the lower load, but comparable SC and CO emission at the higher loads in the case of DME. So conclusion of the study was first we modified the existing diesel fuel injection system, and then we observed the lesser NOx and CO2 emissions and higher SC and CO emissions in the case of DME, but comparable for lower loads. So thank you.
Could you hello? Yeah. Thank you for the presentation. Now, could you tell what can you do about these higher HC emissions? Can you find some diagnostics or some solution to reduce or eliminate the hydrocarbon emissions from DME conversion?
Yes, sir. Because at the lower load, SC and CO emission higher for the DME due to its higher latent heat of vaporization. But we can compensate for it with the addition of globular type of things at the lower loads. So we can increase the in-cylinder temperature and pressure at the lower loads, because from the literature it is clearly shown that for the in-cylinder temperature and pressure curve, the temperature of the DME is lesser than diesel. So SC and CO does not oxidize to its other components, so we can modify it.
Okay, thank you.
Thank you.
Thank you.
Good morning, sir. Myself Vikas. I am going to present toxicity equivalent pressure evaluation for PHE in a CI engine fueled with methanol, ethanol, and butanol blended diesel. Diesel fueled CI engine are one of the major sources of particulate matter emission. PM generation is a complex phenomenon caused mainly by unburned and partially burned fuels and lubricants. As aerodynamic size of PM decreases, PM number concentration increases. PM less than 10 micron aerodynamic dia can pass the nasal passages of the human lungs, and less than 1 micron can reach to alveoli of lungs. Nano-level PM can circulate with blood throughout the human body. ECOC and PM present in PM has been proved to have major health effects: cardiac disease, pulmonary disease, cancer, etc. PM constitutes of elemental carbon, organic carbon, polyaromatic hydrocarbons, trace metals such as nitrates, saturated and unsaturated hydrocarbons, and aldehyde. In this study, we analyzed ECOC and pH through active control of emissions. Partial flow dilution tunnel was used to collect the particulate samples. This sample was chemically analyzed in GCMS.
Total hydrocarbon reduced more than 99% with addition of methanol for 2.5% oxygen. However, total carbon increases with change to higher order alcohol and increase in oxygen content. Similar trend for EC and OC has been observed. Among the blended alcohols, methanol was least effective in reducing the OC proportion at 9% of oxygen content.
In M2.5 2065 compared to 9135 nanogram per full filter paper of diesel fuel of emission has been observed. However, it is worth noticing that the increasing the percentage concentration of alcohol increases the pH concentration in CI engine. In M2.5, pyrene reduced by 38% and fluoxetine reduced by 5% of total pH emission measured compared to the base fuel. Methanol diesel blend with 2.5% oxygen content showed the highest percentage of 10 out of 12 among the measured fuels. These 10 pH compounds increased in proportion by inducing alcohol in diesel for 2.5% oxygen concentration seemed to reduce when alcohol was blended for 5% oxygen concentration and tried to reach nearby composition of diesel pH emission as on intake. M2.5 had given the best of emission in terms of ECOC and measured pH compound. This could be attributable in part to the dilution of aromatics and molecular structure of methanol. B5 had been calculated as lowest and E5 has the highest toxicity fuel among the tested fuels. Total measured pH emission of E5 was 45.2% and 10.11%, lesser than the diesel and M5 respectively. However, toxicity potential of E5 was 14.4% and 14.75% higher than the diesel and M5 respectively. Thank you.
Because can you highlight like what chemical components are responsible for this higher toxicity potential?
Basically, sir, benzene, pyrene, and dibenzopyrene was the main component which were responsible for this higher pH toxicity level.
Can you tell me exactly what is the basis of selecting E5 and all those things? There could be E10 or why did you select E5 and E5 and so on?
Yes, sir. So actually we have selected it based on the amount of oxygen content in the blended fuel. So here it is not like that we have blended 2.5% of ethanol or butanol in the diesel. What we have done, we have calculated the amount of oxygen based on mass in the blended fuel and then we have blended it accordingly. It is reported in previous literature that amount of oxygen, presence of oxygen in fuel can have good effects on polyaromatic hydrocarbons and elemental carbon and organic carbons. Thank you.
Hello everyone. Dr. Parameswaran here from IIT Bombay. We worked on experimental investigation of surrogate fuel and commercially available gasoline tested in spark ignition engine. So we tested the applicability of a surrogate with three components, that is isooctane, N-heptane, and methyl cyclohexane. In this experimental investigation, the various performance, combustion, and emission characteristics were analyzed with the variable speed and rated load condition. Starting from the background and motivation. Gasoline is a mixture of hydrocarbons, mainly alkenes and aromatics, range from C4 to C15 carbonate. The composition of gasoline is highly inconsistent that affect the engine characteristics, mainly like performance, combustion and emission. So in initial investigation in our lab, we found an excellent match between laminar burning velocity of gasoline and the purported surrogate that is used for the present study. The main aim of the study is to investigate the practical application of this surrogate in spark ignition engine. The methodology starts on the formulation of the surrogate. Then we tested that particular surrogate in 3-cylinder 4-stroke water-cooled spark ignition engine. And the emissions were analyzed with the testo gas analyzer. So here is the diagram of experimental setup. In the result discussion, we found that the gasoline surrogate perform better in terms of combustion characteristics like cylinder pressure and heat release rate. We've got better or higher heat release rate from the gasoline surrogate. The reasons behind this is higher H/C ratio. Moreover, the higher octane number of gasoline surrogate. The next point is thermal efficiency and brake specific fuel consumption. In terms of performance, the performance is also better for the gasoline surrogate in terms of higher brake fuel efficiency and lower brake specific fuel consumption. The emission in terms of carbon monoxide is lower. However, due to higher cylinder pressure and higher heat release rate and in-cylinder temperature with the gasoline surrogate, the NOx emissions are slightly higher with the gasoline surrogate. So in short, we conclude that we can use that particular surrogate in place of gasoline. Thank you.
Did you compare your results with the results that are available in the literature?
So we compared the result with gasoline, not with the literature. Initially, we performed the laminar burning. We compared our results with the gasoline, but not with the literature. This is a part of work. Actually, we tested different aromatics in our previous study on diesel engine. Actually, aromatics are somehow important for the propensity of the fuel, but at the same time, they increase some emissions like PM emissions. And similarly, in gasoline, they are required for the. So we have to basically find out that which aromatic is good and which is not good, and we have to remove this as the reminder.
Which kind of engine have you used? Was it SI or CI?
SI. Initially, we tested in diesel engine, a different aromatic, but this one is with the SI.
Okay, thank you.
Thank you, Barunji. So, on behalf of moderator, we are happy to now close this session and hand over to Dr. Akhilesh Pratap Singh for further.
Thank you, Dr. Daya. So now I would like to thank all the panelists and our moderator. Now it's time to honor the panelists and our moderator. So I would like to invite Professor Avinash Kumar Agarwal to honor all the panelists and yeah. I would also like to thank our virtual panelists for joining this session. Okay, so first I would like to invite Professor P. Kusanista. Now I would like to invite Dr. Anil Gautam. And now our moderator, Professor Nidhi Sharma. Thank you. And the co-moderator for this session, Dr. Atul.
Thank you.
Thanks, sir. And I would like to also thank for all virtual panelists who have joined this session. This is the closure of this session. So thank you for all the participants for joining this session. And there is a tea break for 3:30 to 4, and we will again meet at 4 for the next session. That is the session today. Yeah.
So thank you, Amit, Professor Renoir, Professor Franz. It was really a pleasure to have you over virtually, and we look forward to your visit to India, and then we would really have the pleasure to felicitating you in our conference. Thank you very much for your time and your contributions.
Okay, so we will meet at 4 o'clock for the next session. Thank you.
Thank you all, and bye-bye.
All done.